Okay, in this slides presentation, we're going to talk about some of the very early medical diagnostic support systems and why they're important to think about, even though they're not systems that are in use today. So the root of kind of the big explosion of work on computerized medical decision support traces back to 1959 when Robert Ledley, an electrical engineer, and Lee Lustig, a radiologist, published two articles. One was in the journal Science in July, and the other was in the Proceedings of the IRE, which is, I think, probably Institute of Radio Engineers or something like that, in November. And this launched the publishing discipline of computational diagnostic decision support systems. So what did they talk about? So their article, Reasoning Foundations of Medical Diagnosis, laid that there are really three mathematical principles that lie at the root of how medical decisions are made. The first is symbolic logic. The second is probability, and the third is value theory, of the specific instance that they were looking at of game theory. Now, you may not be as familiar with game theory as you are with symbolic logic or probability, but it's really a way that we assign value to different outcomes. So we could think of an outcome that's very desirable. The patient lives, but the cost is so high, and maybe the morbidity of the treatment is so high that their life, their quality of life is poor, and so we may assign a low outcome to that as we combine the different values that go into achieving the outcome. So we're going to start off with probability theory, and this is just very foundational for all decision making, and certainly in medicine. So this is from a recent book, Thinking and Reasoning: A Very Short Introduction. It is essential, for example, that doctors know how to make correct Bayesian inferences when interpreting diagnostic tests, and that courts of law know how to interpret statistical evidence, as in the case of DNA tests. And if you look at any look through news stories, it's obvious that neither physicians or lawyers are always making good interpretation of probabilistic evidence. So why is probability so important? Well, it's important because in medicine is largely, and healthcare more broadly, is largely a matter of managing uncertainty. And probability is our most rigorous manner of reasoning with uncertainty. So after the Ledley and Lustig articles, there were a series of papers published in the 60s and early 70s that used Bayesian probability and statistical methods to diagnose various diseases. So the first was from Homer Warner, who we have met previously, and so he published a paper in the Journal of the American Medical Association in 1961, and a later follow-up in the Proceedings of the New York Academy of Science that looked at Bayesian diagnosis of cardiac conditions. This was followed up a few years later by Gorey and Barnett, who were at Harvard. Again, cardiac diagnoses. And then in the United Kingdom in 1972, a group that was looking at Bayesian diagnosis to look at diagnosing causes of abdominal pain. So what are the things you need to know in order to create a Bayesian diagnostic system? Well, first off, you have to have an exhaustive and an exhaustive list of disjoint diagnoses. So every possible outcome has to be in your model, and so there might be an other or a normal that captures everything else that's not in the other enumerated diseases. And disjoint diagnoses mean you can only have one. I can't have both disease 1 and 3. If I have what's called disease 1 and 3 in my model, I really need to come up with a new disease that is the combination of those 1 and 3. And I also need to know what the probability of some symptom, which I am labeling S here, so this is a symptom, given some particular disease. So if the disease is COVID-19, what percentage of the people with COVID-19 have a fever? Or what percentage of the people with COVID-19 have a dry cough? So this is our conditional probability, the probability of some symptom S, given that I already have a disease D. And further in their models, let me just see if I can erase that. The next assumption that is made is that if I have two symptoms in a disease, so like a fever and a cough, given that I have the disease COVID-19, then having S1 and S2 are independent of each other, given that I have the disease D. So that would be expressed that the probability of S1 given D, that the probability of S1 and S2 given D is equal to the probability that I have S1 given that I have D multiplied by the probability that I have S2 given that I have a disease. So these are the requirements of the model as they were implemented then. This conditional probability independence is something that's going to come up over and over again in Bayesian diagnosis and different methods people have proposed to try to deal with that. Okay, let me move. Let's see, get my. See if I can get that back. Okay. Now, what are the challenges with this approach? And this is from an article by Shortliff and Buchanan that I'll reference shortly. So the use of Bayes' theorem requires either large numbers of valid background data or numerous approximations and assumptions. So the availability of data to compute these various probabilities, or numerous approximations and assumptions that may be questionable of their validity. Okay, further, although conditional probability provides useful results in areas of medical decision-making, such as those we have mentioned, vast portions of medical experience suffer from having so few data and so much imperfect knowledge that a rigorous probabilistic analysis, the ideal standard by which to judge the rationality of a physician's decision, is not possible. And so if I come back here to this model, one of the big problems is this assumption of conditional independence. And so if these variables really are not independent of each other, as we include both of them in our model, we're really kind of double counting the same evidence. And so the tendency is to come up with overconfidence in a computed probability or a larger probability than is actually warranted by the data. Okay, so we don't necessarily have all the data that we need to compute these probabilities, and the assumptions that we make to get around that problem are sometimes problematic. Well, there's other issues. First off, there's many studies showing that humans aren't Bayesian. When given evidence, we don't compute the evidence in a Bayesian manner, and this is a bad thing. We do know that Bayesian is optimal in how we want to be doing things, but what if you're interested in how people reason? We don't. So these researchers are artificial intelligence researchers, so they're not only interested in a medical solution, they're interested in understanding how humans think. And further, what if your diagnostic decision support system doesn't perform as well as a human, as a non-Bayesian human? Well, we would want to be Bayesian if we could, but we can't. So can we learn how to make better suboptimal decisions if we study how humans are making the decisions that they are making. And so these were some of the thinking behind one of the next kind of milestones in medical diagnostic decision support systems. And this is a system called MYCIN, which was developed by Ted Shortliff, who was a MD, PhD student at Stanford University, and Bruce Buchanan, who we've met previously in this course, who was his research advisor on this. And so they came up with a rule-based system, but that also incorporated heuristics to represent uncertainties and how humans dealt with uncertainties. And so they came up with measures that indicated whether there was increased or decreased confidence in a particular conclusion given various evidence that were presented. And as I said before, heuristics, Bruce Buchanan was very interested in heuristics, and I think if you look at their paper, he was in a heuristics lab, and hence his recommendation to get Poya's book, How to Solve It. So here's an example of one of the rules they came up with, and they started this process that's referred to as knowledge engineering, where you would bring in various experts, in this case like infectious disease experts, and work with them about what are the conditions, the findings that you would be looking for that would be caused by different bacterial agents. So in this case, Rule 507, if the infection, okay, so there's these ifs and then there's a then. So if the infection that requires therapy is meningitis, and if the organisms were not seen on the stain of the culture, the type of infection is bacterial, the patient does not have a head injury defect, and the age of the patient is between 15 years and 55 years, then the organisms that might be causing the infections are these things that I am sure I would mispronounce. And so a couple of things to be aware of here. They're trying to create these kind of self-contained pieces of knowledge that don't interact strongly with other collections of knowledge that they have in their knowledge base, so that it's easier to maintain. So if they decide to edit Rule 507, it doesn't have unintended consequences on the execution of Rule 510, 613, etc. This system they created was programmed in Lisp, and it used a method of reasoning called backward chaining, where they'd basically have a conclusion, and then they would look for evidence in the patient's data that would support that conclusion. And if there was an absence of evidence to support it, then you would rule out that conclusion and move on to another conclusion. Well, so those are kind of the two foundational principles of decision making that were laid out in the 60s and 70s. We have Bayesian reasoning, and we have rule-based heuristic reasoning, as illustrated with MYCIN. And so then in the 1980s, people started working on early general medicine decision support systems. And this differed from, like, MYCIN was a very narrow domain. It was looking at microbiology and antibiotics. The Bayesian work by Homer, Warner, and Octo Barnett were narrow problems of cardiac disease. This would be coming up with diagnostic support systems that addressed all of general internal medicine, the things that you would go to see your general practitioners about. And so there were, we can briefly talk about 4 of these, really kind of about 3 of these, and some of the evaluations that were done with it. So there's a New England Journal of Medicine article that evaluated these 4 general diagnostic support systems. And that's why I'm listing them here. The first is DXplane, which came out of Octo Barnett. I'll introduce these people in a second. The second is ILLiad, which I think I've misspelled here, which comes from Homer Warner, Metatel, and QMR. So Iliad and Metatel are examples of Bayesian systems, and DXplane and QMR are more of these heuristic, rule-based methods. But none of them are pure. They all mix aspects of both decision milieus in their approaches. So DXplane is a product of Octo Barnett. He's one of the really early contributors to informatics, and he was at Harvard University and Massachusetts General Hospital. So some of the things that his things would be kind of important to understand, be aware of in a historical perspective, is he was the co-developer of CoStar, which was an early EMR that was used in some of the Harvard hospitals. He supervised the development of MUMPS, and I list like here are the kind of the actual published creators. MUMPS is important because it is a database system that's still used today, and probably most important to people in this class is that the Epic commercial EHR is built up around MUMPS. So DXplane is a non-Bayesian decision support system with heuristics for modeling uncertainty in the vein of Mycin. And in a JAMA article, they explain what their motivation for developing this is. DXplane does not attempt to make a single diagnosis to mimic the behavior or replace the judgment of the expert clinician. DXplane has a less ambitious but perhaps more attainable goal to suggest a list of diagnoses that should be considered given a particular set of signs and symptoms. So it's a suggestion system to help a clinician think through what is before him or her. So Iliad, again by Homer Warner, it's a little bit different in that it was explicitly, the development of it was explicitly for medical education. So Homer thought that medical students weren't very good at learning how to diagnose. And so he wanted to develop a framework that would help medical students think about the data they have at hand and then think about what would be the next best step for a test or whatever to reduce the uncertainty that they were facing. And as with almost all things with Homer, this was a Bayesian approach, although there were heuristics. And they came up with the concept of knowledge frames, and this was to explicitly deal with this conditional dependence issue that I mentioned previously. And within these knowledge frames, you would have a mix of logic, rules, and probability. And then all the knowledge frames were, the information from all the knowledge frames were integrated together in a Bayesian framework. Okay, the fourth one is QMR, which stands for Quick Medical Reference, and its primary developer was Randy Miller. And it's an outgrowth of an earlier diagnostic decision support system known as Internist One, which was created with Randy Miller and Myers and Popel at the University of Pittsburgh, which is where Randy Miller was at the time. It is a non-Bayesian decision support approach that uses heuristics in the vein of Mycin, and it has two concepts of uncertainty. One is evoking strength. So if this finding is present, it's really strongly associated. It evokes a strong confidence in a particular conclusion and a frequency. This finding is very frequently associated with this particular disease, or less frequently. So there was an evaluation of this done in the New England, of these four decision support systems in the New England Journal of Medicine in 1994, and I have a link to the article. The article is accessible at least through the University of Melbourne library system. It may be open source, I'm not positive. The evaluation was done independent of the developers. None of the people on the paper were the developers of these four techniques. They picked purposefully diagnostically difficult cases thinking that these would be situations where a physician in reality would seek the help of a specialist consultant. And the performance wasn't, outstanding. And an editorial that went along with this paper, gave them a grade of C. No single computer program scored better than the others on all performance measures. Among all cases in all programs, the proportion of correct diagnoses ranged from 0.52 to 0.71. And the mean proportion of relevant diagnoses, every one of these systems is creating a list of possible diagnoses, not just the top choice. And the mean proportion of relevant diagnoses ranged from 0.19 to 0.37, which would be viewed as poor performance. On average, less than half of the diagnoses of the expert's original list of reasonable diagnoses were suggested by any of the programs. However, each program suggested an average of approximately 2 additional diagnoses per case that the experts found relevant, but they themselves had not originally considered. So, that being said, I don't think they evaluated, and that you would want to know, is if you presented these challenging cases to an average general practitioner, what would their performance be? I have to check back on the paper whether that was done or not. Okay, so this evaluation that was done in 1994 prompted another one that was led by Chuck Friedman, who's an important name to know in medical informatics and did a lot with developing methodologies and promulgating methods for evaluation in informatics. And so he thought, this previous study was looking at, how does a computer just perform on its own? You put the data in and then it tells you something. But in reality, they would be systems that would be used interactively with a clinician, and somewhat akin to a textbook or a reference. A physician is going to look something up, and do they come up with better decisions if they have this resource than if they don't? And so he designed a study that was looking at the interaction. Does the computer help the clinician perform better than the clinician without it? And again, this is another study that was, in this case, they took 2 of the systems. They took QMR, which is the heuristic rule-based approach, and ILLiad, the Bayesian approach, and did a study where they looked at, again, they selected a variety of difficult diagnostic cases, and they looked at what was the performance of an experienced physician, a resident, which in Australia you'd refer to as a registrar. It's someone that has received their medical degree but are in training in the specialty that they've chosen, and then medical students. And what they found is that if the clinicians, if residents or medical students used either QMR or ILLiad, their diagnostic performance improved. And, perhaps not surprisingly, the largest effect was seen with students. Students saw a large jump in the quality of their diagnoses. And this is both measured, like their confidence in their conclusions and the correctness of their conclusions. And so this, really kind of reinforced the idea that these tools should not be viewed as an oracle where you go, and this is, the Greek oracle at Delphi, you don't go to them and then they tell you what the answer is. It is something that you work with to make your decisions. And again, really maybe the best role, or like certainly an early role for these, would be improving the education and helping medical students learn how to diagnose better.